So in the stress consideration chapter, we did thermal, we did stress concentrations, we did combined materials, and we did Poisson's ratio, I think. Right, so those are all just different kinds of stresses to consider. Torsion is also a new kind of stress to consider. It's like a shear stress. So if you understand shear stress, that shears off material, right? Like just shears it straight off. Torsion does the same thing. When you twist something to failure, it creates a shear-like failure. This is a drive shaft that's been torsionally failed. So it literally twists it off and shears it in this plane here. Okay, so it's it's not like we chopped it this way, right? We didn't have a big load that chopped it down, but we literally twist it until that geometry literally fails. It's called torsion. It's pretty cool. You know how much force it takes to twist that thing off? It's incredible. We can calculate. All right, so it's something like when you have rotational loads, torques, torsion happens. So that's a load we haven't dealt with yet. We've just had these forces going down. We've had forces going up. We've had tensile forces and compressive forces. We've had all of these kinds of distributed loads, but we have not dealt with a rotating load. As far as stress goes, we did this in statics, right? We calculated moments. It's the same thing. Unfortunately, as we go into strength of materials, we don't call them moments, we call them torque, which is the same thing. So why they didn't use M for moment, I don't know. Some other scientist came up with this and he called it torque, or she. So we just need to learn the equation and learn how to calculate it, right? And compare it to the material properties. So the equation gets the same symbol as shear. Same symbol as shear, but it's torsion. Just think torque, torsion, torque, torsion, torsion. And the equation is TC over J. So here's the first introduction of J. And T for torque, that's the same as moment. You've had that before. C is the distance, so the cross section is what fails, right? It's this round piece that's going to fail, the cross section. So when we look at the cross section, C is the distance from the center to the outermost fiber, C. So if it was a square shaft, where's the distance from the center to the outermost fiber on a square? Yeah, the corner. That would be C. So it's the largest distance that you can find in the cross section. That's what C is. If you have a complicated shape, which we will not have, then you have to figure out like these distances. You have to locate the centroid, go through that whole mumbo jumbo again. Once the centroid is located, then you can find that largest distance to the outer fiber. It's that outer fiber that's going to shear first. So that's why we calculate it out there. Does the fibers right here at the center, right at the very, very center, they see zero stress because that's the center of rotation, right? So it's those outer fibers that feel the most of it. So T is torque. If we don't know the torque, we have to calculate it. This example problem, I've given the torque at 600 foot-pounds. Right? But if you're given like loads out at the end, then you just have to calculate a torque.
Is that J thing under it, deformation?
Yeah, no, J is the polar inertia. So we've dealt with I. That's the rectangular inertia, IX and IY. Yeah, we've all done that one and we know how to do it. How do we calculate I?
Back of the book.
What's the easy way? Yeah, back of the book. Go look it up. Hopefully we could just do that, not have to go back to the inertia formula, right? Same with J. Back of the book, Same table has J values. Polar moment of inertia. Formulas for different shapes: half circle, pipe, square, semicircle, rectangle, round. Right? What is it? It's the inertia about the z-axis. So we did Ix, we did Iy. Now, because Ix would be like right here, this would be like y, and this would be z. So it's the inertia involves the rotation effect. You can also get J, this is just a fun fact, trivia for at the next party you're at, you can share this trivia. Ix plus Iy equals J. So if you don't know J and you don't have a formula, you calculate Ix and Iy and you add them together and you get J. But J has its own formulas that we can use. So we just look it up. So this is an equation we just learned to run. Like, oh, we have to know the torque in whatever piece that we're working with. So if the torques change, like in a drive shaft, that's the most common one, where you have a shaft and there's a bunch of different implements being pulled off the shaft, right? Like your car is this way where it has a bunch of things that are being driven off of it, the alternator, all kinds of things off of different pulleys and things. We just have to know what the torque is in the section that we're doing the analysis of, right? So we'd have to know what the torque is here, and then maybe what the torque is here, here. If the shaft is not changing in diameter, then we just need to know where the largest torque is and calculate that, because all the smaller ones will be fine, right? So if we're given something like this, we have to go back to our statics and say, oh, it's in equilibrium, it's got to be. So if I just look at this left side, the torque in this shaft would be 600, or if I just cut it right here, look at the right side, I can add these two together, the torque in this would be 1800, right? We go back to our statics to get it. So you got to know the torque in the shaft where you're doing the analysis. This one's pretty straightforward. There's only one torque and one shaft. And then some kind of anchor, right? It's like fixed. So if it was free to rotate, we wouldn't have any torsion, right? It's just free to go. So it's 7 inches long. It is a 1/4 inch in diameter. It's A36 steel and 600 foot-pounds of torque. So it's just a new kind of load, and we have to figure out the new kind of stress. So it's going to be 600 foot-pounds. Again, you're going to want to write your units out and make sure they all work, because we're looking for PSI, right? Pounds per square inch, or KSI, kips per square inch. But we want the units to work out so we get that unit. So if I put the torque in as 600 foot-pounds, and then what would C be? Yeah, half of the quarter, 0.125 inches. I already have a foot-inch issue. And then we're going to put J in, and J is most likely going to be in inches, right? So what's the inertia equation for a round? We'll look it up. Pi d to the 4th over 32. Pi diameter 0.25 to the 4th over 32. That's J. It's not all going to work out to PSI, right? Because we have this foot in here, so we got to get rid of the feet. 12 inches per foot. So I'm going to write the 12 inches above and 1 foot below, and then the feet cross. Now I have inches squared above and inches to the 4th below, leaving pounds per square inch, PSI. So just make sure your units work out when you're running this equation. Aiden, what do you get for your number?
I haven't gotten it yet.
Okay, can't wait. I just made this up, so I'm getting a big number.
Yeah, I gotta.
I'm getting 2.3. Actually,
2 million.
Yeah. Yeah. 2.3 e to the 6 psi. So it's a 1/4 inch shaft, tiny little shaft, and 600 foot-pounds, whole bunch of rotation. Way over the 36,000, like stupid over, right?
Thanks, so you get clear instead of leave them like I'm gonna.
It's all gone. So then you can always ask the follow-up questions. Okay, that failed. How much could it carry? How much torque could it carry? How would we do that? So now we want to know torque.
We're gonna solve the equation,
Yeah, what do we put in here though?
the max.
Yeah, the maximum stress we're willing to let it go to. So with no factors of safety, we put 36,000 in there, right? With factor of safety of 2, we put 18,000 in there, kind of thing. So let's just put 36,000 in. So there's that. I want to isolate T. So I'm going to move C down and over, and C was 0.125 inches. And then J, right, comes across and multiplies. So J goes in here as a multiplier. And that's going to equal torque. So it would be torque is the stress times J divided by C. And that'll give us the allowable torque on this 1/4 inch shaft. With no factor of safety. Anyone get 110?
Yeah. That's.
And since everything's in inches, I got pounds per square inch, I got inches to the 4th. It's going to be torque inch pounds. Okay. So the pounds are on top here. This inch is actually down below here. So again, pretty simple formula, and you can massage it to do a number of different things. You can calculate how much torque it could take or the existing shear stress. You could even do some work with the design, like how big of a shaft, but that's a much harder calculation. If we don't know the shaft diameter, like if you got a torque, say I do have 600 pounds, and I know the 1/4 inch won't take it, how big would the diameter have to be, right? Well, that's in two things. That's in J and that's in C. So it becomes a complicated kind of serious algebra problem. You could do it, right? You just have to put in J, which is the pi unknown. You could put D in here, and then this would become D over 2, and then you have to do the algebra to solve for the diameter. It's just a lot harder process to do. Good so far? All right. Let's do another one. So we'll put a shaft and a couple pulleys. And we'll have 150 foot-pounds here. And then we'll have 70 foot-pounds here. And we'll say that both of these kind of ride on a bearing. So this thing's free to spin. And we'll make it a 1.5 inch diameter stainless steel shaft. There's 3 sections to the shaft. I'll give you a couple seconds to draw. Don't know their lengths because you don't need lengths when you're calculating torsion. You need lengths when you're calculating angle of twist. So that's deflection, right? So that last shaft we did, we'll calculate the deflection on it in a second. But if this is free to spin in this bearing, and it's free to spin in this bearing, I got 150 going clockwise, and I have 70 going counterclockwise, right? Those directions are different. What's happening out here at this section of the shaft? A. Free to spin and free to spin. Is there a torque out here? No. That free end is just spinning away, right? So all along here, traveling all along here in the shaft, there's no torsion. Same with out here. No torsion, it's just free to spin. It's not, there's no load. I mean, I'm sure there's a little drag in the bearing, there always is, but very little. Like not even probably a foot-pound out there, right? And then what's happening in here, in this B section? Yeah, so that's where we get the torsion. We have 70 going this way, 150 going this way. If I split it, then what's it gonna feel? Like if I just section it, right? It's gonna feel the difference between this 150 and the 70. There's 80 that's being pulled off, right? So inside this area, there's gonna be the difference between these two 80 foot-pounds. So that's kind of how you have to look at it, like, oh, what's going on between the two, right? It doesn't feel 150 because it has 70 going the other direction.
So those wouldn't be added together, they would be subtracted.
Yeah.
'Cause even if they're going in two different directions.
They're going in two different directions, then you have to think about like, oh, one's just going harder than the other one, same kind of thing, right? Yeah. All right, so let's calculate this. Torsion equals TC over J. Torque is 80 foot-pounds. I know I'm going to want that in inches, so I'm going to go 12 over 1, 12 inches per foot. And get rid of that foot right away. And then I need C, which is half of the 1.5. And then J again. Round shaft, pi d to the 4th over 32. You want to get that number?
Yeah.
Oh, good. And what do we have for yield to stainless? Stainless steel, I think it's the same. I think it's. Oh, it's higher, 42. 40. My book has 40. PSI or 40,000 PSI. So no problem, right? 1.5 inch shaft carries a lot of load. That's almost the size of this broken one that we have floating around. Once you have the torque, that's pretty straightforward. Good? All right, so let's go back to the one that we did here, where we calculated how much it would take. All right, so we put in the yield, 36,000. Calculated the torque at 110.45 inch-pounds. So now, often you want to know, like, how much did that deflect the shaft? Because it's trying to rotate it, right? So what happens is a shaft that's loaded like that, I'll say that's my base point. This is what happens to this point. It rotates. That's called angle of twist. So if something was actually fixed to the shaft, right? Like a bolted connection of some kind, and you put this kind of moment on it, everything's gonna move, right? It's gonna rotate. Deflection happens. So we can calculate the angle of twist to see how much that shaft is gonna rotate and if things will still line up or not. So to get angle of twist, the equation is, and they use theta, torque, length over polar moment of inertia, which we just talked about, and a new material property, G. G is like E. E was the modulus of elasticity. That had everything to do with bending, right? We're going to use it in bending big time. And also in pulling things apart, E was involved. Well, twisting, it's a different material property. It's G, the modulus of rigidity. Again, it's a material property. So if this thing's made out of A36, then it's got a G value, right? If it's made out of stainless, it's got a different G value. So most of the equations are going to have load, geometry, which is like the area, cross-sectional area, and then material property. Those three things kind of have to be in there to know how these materials react. So modulus of rigidity. So we should be able to calculate this. Our torque, our acceptable torque was 110.45 inch pounds. Our length, I did give in the problem, was 7 inches. 7-inch long thing. And J for the round shaft was that pi d to the 4th over 32. We're back to the 0.5. And then G for A36. So we go look up G. For standard mild steel A36, it's 12,000 KSI. 12,000 KSI. So we don't have kips going, we have pounds going. So we can put in 12 million PSI. Because then the pounds and the pounds work together. So that's super important because for angle of twist, we want all the units to cross. Okay, so let's see if that happens. The pounds and pounds cross, right? Inches to the squared denominator in the denominator, this flips up top. And we have inches squared up here, plus this, inches to the 4th on top. And we have inches to the 4th on the bottom. So angle of twist is unitless. What is a unitless angle? Anyone know? Radians, yeah. So the equation gives us the angle in radians. I know, sad face, I agree. All right, so what is it? Anyone get him a number here?
168.
0.168
Yeah.
radians. Most folks, and even most engineers don't want it in radians. Like, this is not what we want. So then we go through the process of converting it to degrees. Anyone know that conversion?
Isn't it like times pi over 180 or something?
That's from degrees to radians, right?
So what's the relationship? How many degrees are in pi?
60. No, 2 radians. No.
2 radians and 360. 1 radian and 180.
Yeah.
I don't care which one you remember. One of them though you need to remember. Right, I do the 180 in pi. So that means that to get rid of the radians, you have to go, because pi's in radians, right? You have to put your pi down below and your 180 above. So pi radians is 180 degrees. Then the radians cross.
Sounds close.
So don't you, yeah, you multiply by 180, divide by pi to get to degrees. Anyone got a number? 9.63-ish, right?
Yeah.
9.63 degrees. That is how much it twists. Now, if you wanted to know where point A ends up, down here, right? Because A and A goes to there, then you have to calculate a circular distance from your 9.63 degrees. So there's more to do if you actually want to know, like the displacement of A. Because we just got this, right? The angle is 9.63 degrees. We're not going to do that quite yet, but we'll do that at some point. Because really what you want to know on the outer surface is like, how much did that change, right? We know angle of twist now, but now we need to do a little more math to figure out like, oh, how much did it change out there at the circumference of this little quarter inch? Not much. A little quarter-inch shaft, 9.63 degrees. It didn't move a whole lot, very little. So this is pretty big. Like that's a big angular change. It's almost 10 degrees, right? But that's because we went right to the limit, right to 36,000. Like this comes down, as this comes down, factor safety stuff, you can really bring that angle twist down. So just keep in mind, when you put in the max, you're gonna get big changes. Like you're right at the edge of yield. It's good. All right. So that's torsion. You have a homework set on that. And then you have a homework set on bending moments. So I need to talk about that a little bit. So we got to take a breath and then shift a little. Pushing you forward.
How did the drive shaft stand? Or
The one that was given to me
yeah.
was on an implement. I want to say it was some big tiller being dragged behind a tractor, right? So something that was tilling the ground, and then there was a bunch of wire in the ground, and it locked that tiller up, like just locked it. And he said it was the tractor was fully loaded, like he had it full RPM, just grinding on the earth, and just took it out. Older system that didn't have any safety features, kind of thing, you know. Good old tractor company. Just tear shit up. The reason I'm pushing it forward is we've actually had this before. The stuff that I'm going to review is kind of review of statics. So we haven't done it in a while. So that's why I'm going to kind of push you into this. This is working our way towards beam analysis, which is what's next. So we have to remember how to do basic statics and find out what's going on at roller C and at pin A, and then work our way towards calculating a bending moment inside this beam, which we've not done. So the first part we've done, that's statics. But the second part is trying to understand what the beam is feeling at certain spots. Right? Because then that will work us towards bending stress. And that's really what we want to get to with beams, is understanding bending stress and shear stress. Okay? So I'll let you capture this beam real quick. It's 10-foot overall length. The roller's 2 feet from the end. It's got a distributed load on it, 100 pounds per foot, pile of plywood or something. And what we have to calculate is what's going on at reaction at pin A and roller C. And then we're gonna also find some bending moments within the beam. Like what's it feel? You know, at 5 feet, what's it feel? Kind of thing. So let's go through it. Let's remind ourselves how to do this. Anyone remember what we do first?
Multiple distributed load.
Concentrated distributed load, we could do that, or free body diagram, either one, same thing, right? Because free body diagram would have a concentrated load. So free body diagram, how many reactions go in at A? Two. So it gets an X and a Y. I'm gonna guess at both of them. What's AX equal to? 0, because there are no X forces in the system. Good. How many does a roller get? 1. I'm guessing it goes up. CY. All the loads coming down. You know, unless this was hanging way out here, then this could be like trying to rotate it, and this could maybe go down, right? But I'm gonna guess that it goes up. And it is a guess, and then you hope the math figures it out for you. All right, concentrating the distribution. How do I do that?
The distribution weight times the.
Area of the load curve. So this load curve is a rectangle. So it's area of the rectangle. If it was a triangle, it's area of the triangle. If it was a half circle or a parabolic curve, then it's area of whatever curve you're given. Okay? So how far is it along its base? 5 feet. How tall is it? 100. Right? So 5 times 100 is 500. And where does it go? It's right in the geometric center. 500 pounds. If it was a triangle, then it goes through the geometric center. You got to look that up if you don't know it. If it was a parabolic function curve, then you got to look up where that geometric center is and put it there. A rectangle is pretty simple. It's 2.5 from this side and 2.5 from this side, right? Yep. Good. Free body diagram done. Now what?
Find the AY or CY.
Yep. Go for AY and CY. We have 3 equations. Some forces in the X, some forces in the Y, and some a moment. And they're all equal to 0 because this is statics. Now, there are no forces in the X, so that one doesn't do us any good. There are 2 unknowns in the Y. So we could write that formula, but we're not going to be able to do anything with it. That leaves us with summing a moment. Yep. Where do you want to do it?
Okay.
Sure. The notation was some moment at A. This is collecting out of those rotation forces, right? Everyone remember this? Kind of fogginess? Do the 500 first.
500 times 8
500 times, careful,
divided by 8.
not 8.
I forgot.
It's from here to here and from here to here. So it's 5 plus 2.5, right? 7.5 feet. That perpendicular distance. And then how do we put the sign? What do we know about the sign of a moment? Yeah, counterclockwise is positive, clockwise is negative. So this is rotating clockwise, negative. And then what other force creates a moment about our point A? Because we're doing it A. CY. And that is CY times 8, Colton. And that's positive because it goes the other direction, counterclockwise. And AY drops out because it goes right through the point. Oh. I'm relying on you, my calculator died. Can almost do it in my head. It's gonna be a little less than 500.
468.75.
Yeah. And then how can we get AY?
So force from the Y.
Yeah, some forces in the Y. I know I got 500 coming down. I have 468 going up. And I need a little bit more and AY going up, right? To balance this thing out because everything is equal to 0 in statics. $500 goes down, the 468 goes up. And AY goes up. And all that's equal to 0. That gives me AY at
31.25.
your calculator's working good today,
Yeah, I forgot to square the diagram was.
Aiden. I love that you're persistent enough to figure it out. That's a goal in engineering life. You gotta know why. All right. Everyone okay with this? This is like a refresher. All that you've had in statics. What I'm gonna do now, in just a couple minutes, is talk about bending moment, like the moment inside the beam. Now we know all the forces, right? We have them all collected. We know what's going on. But what we gotta know is what is the beam feeling at certain locations, like at 5 feet from the left side. We almost always talk about from the left side, and I think it's because we read left to right. So you'll even see the book says from the left, do it from the left. The problem's gonna say find the moment 7 feet from the left, right? So we can just pick spots. There'll be a way in the future where we just learn all of it at once kind of thing. But right now we just want to understand the concept of it's bending, right? But what's it feeling at certain spots? So at 5 feet, the way you do this is you literally cut the beam. You section it wherever you want to learn about it. So I'm going to cut it at 5 feet and I'm going to draw a new free body diagram. So this is my 5 foot section. Right? And you put all the forces on that exist. There's one. 31.25 pounds. There's nothing else. That's it. Everyone agreed? We're right before the distribution, but we're not to the distribution yet, so it does not show up. So this is a at 5 feet analysis. So now I have to put this system in equilibrium. And I do it with two things. I do it with forces because all the forces have to be in equilibrium. So if I got 31.25 going up, what does the beam feel at 5 feet going down? If this thing's in equilibrium, 31. It's gotta be. 31.25, that's called shear force. V. So at 5 feet, it feels this two opposing forces up and down, right? And we're positioning ourselves here. That's the thing you have to, wherever you cut it, that's where we're learning things about. So shear force 31.25. And it's down, and we'll learn what down means later, but it's either a positive shear or a negative shear, right? The other thing that would have to happen here at my 5 foot is we would have to resist the rotation that this is trying to create. That's called internal bending moment. And it's usually drawn with a rotating moment sign. And it's going to oppose the external rotation. So the 31 is trying to rotate clockwise, right? So the internal moment at 5 feet has to rotate counterclockwise and put it in equilibrium. 31.25. It's a moment, so it's force times distance, 5 feet. We calculate the moment at the spot. And we know moment equals force times distance. So that gives me an internal resisting moment of, oh, I can't calculate it.
156.5.
156.25, and the units are foot pounds. That's what the beam's feeling inside. Cool?
The shear force, that's different from.
That'll be shear stress that we'll calculate, yeah. So we're gonna want to know 2 things: bending stress and shear stress at any point in the beam. So this is like the manual way to do this, or the by hand way, where you pick a spot and you do the moment, right? You figure out the bending moment. Like you could do it at 4 feet. What would it be? It would be 31.25 times 4, right? You could do it at 3, at 2, at 1. You can do it at any spot you want. If you go the other direction, now you start to pick up the distribution and you have to include it, right? So if I went, I'll go 7 feet. Distribution shows up. Right, where this is 5 feet, this is 2 feet. And this distribution is 100 pounds per foot. And here's my cut. So now I'm at 7 feet. You literally just do the same thing. You figure out, I got all these forces. Now I got 31.25 going up, and I have how much coming down? 200 coming down. And those oppose each other. So I end up with a down. Notice that the shear switched. And that's going to be 200 minus the 31.25. Have that number for me.
168.75.
Say again.
168.75.
168.75 pounds of V shear force. That changed dramatically. It was 31, right? Now we have a lot more shear because of that distribution. And now we have to calculate a moment. Well, we still got the 31. So this would be moment at 7 feet. We have the 31.25 times 7 feet now. Right, and that one is clockwise, which is negative. I need to kind of keep it straight because these are going to be different directions. And then I have this distribution that creates moment. How do we deal with the distribution?
Concentrated.
We concentrate it. So you got to concentrate this new little distribution. So it's 200, right? 2 times 100, 200 pounds, right through the middle. How far away from my spot? 1. So 200 times 1 foot. And that rotation is positive. Or counterclockwise around my spot.
What direction did you say was negative?
This one,
For a movement? Okay,
clockwise, negative.
alright.
This one goes this way, positive.
I just need to fix it then now, because Tom says it doesn't matter,
It doesn't.
because you can do it either way.
You can.
Yeah.
It just switches a sign. What's important is they're not additive. They're subtractive, right? One is fighting the other one. And it doesn't matter, but I just go with the book, and the book went counterclockwise is positive. So. Anyone got a number on that?
18.75 negative.
18.75?
Yep.
Yeah,
18.75.
yeah.
Yeah.
Foot pounds?
Yes.
Yep.
And it's negative.
It's negative. Notice how low it is compared to the last one. Right? So this moment thing is actually getting kind of better as we move across. It's getting less. And that's because this deflection happens like this, right?
We can't see.
The deflection of the beam looks something like that. Yeah, so where that deflection is max is where your maximum bending stress is. It's in here somewhere. And it's gonna be less. The most kind of right in this region, kind of right where this 5 was. So it will go up and down based on the load and how the load is fighting each other. Right? And the deflection curve, like how this thing bends, kind of gives you a hint as to where those maximums are.
And it's not necessarily the underneath.
No, it's not under big loads, not always, right? Because we happen to have a support kind of under this big load that's helping hold it. So. Yeah,
The further away that.
it's tricky, yeah. Like I bet there's some out here, this bending moment's gonna go back up out here because this is kind of cantilevered out, right? Again, this is like the manual way to do it, like you can pick a spot and get the moment. You can pick another spot and get the moment. But we'd have to do so many spots to find the max, so it's not the perfect way. We'll do the perfect way probably Thursday, maybe. We'll see. We'll see how the homework goes. All right, that's it. You have one of these to do. So the homework is chapter 12, 1 and 2. That's torsion. And 13, just number 12.
Number 12, you said?
Yep.
1, 2, 12, 13.
Just 1, 2,
1 and 2. Out of chapter 12.
Yeah.
And then out of chapter 13,
Okay.
12. Sorry, there's a lot of 1s and 2s there. This is a test. Oh, good. We are done. Big day.
I don't feel good.